In this example, I'm going to show how to use the Computational Fluid Dynamics module inside the Eushaw Dynamics software to design or analyze the previously designed flow control device using the Computational Fluid Dynamics to calculate the performance characteristics of the flow control device and import these flow characteristic charts in the format that Eushaw software can read it. The whole process is automatic, but the user should define the geometry first. So in this example, I briefly initially talk about what are the bases of this analysis, and then I'm going to show one short example using the Eushaw Dynamics software. In this example, I'm only going to talk about the chamber type, the FCDs, and not it would be another example talking about Venturi type and other different type of FCDs. So the chamber type FCDs are a series of chambers that in each of these chambers, regarding the vortex happens, there is a delta P happens in every chambers. And as you go this direction, you build up these delta P. And so the famous type of this type of the chambers is the select that provided by Baker Hughes. But there are other types, but as an example, I just brought in the Baker Hughes select one. So the performance chart of these chamber types are mostly represented by pressure loss coefficient. And this type of the curve is pretty much the same for different restrictions of these chambers because these coefficients or pressure loss coefficients mostly governed by the geometry, not the restriction. But the up and downs and this pressure coefficient is 35 at this location would be different at the different restriction, but the general shape is consistent. And as you see at this small Reynolds, we have a high pressure loss coefficients, and then we have a drop, and then we start building up and we reach a steady state. But in Eushaw software, in the CFD module, we calculate the pressure loss coefficient, but there is another parameter that we calculate, and we call it FCD Restoration Factor. And this is the factor that mainly required by the software to calculate delta P as a function of rate. And this is the factor that we match it in a way that the software can read and use it for reservoir engineering aspect and interaction between the FCD and the reservoir. So what is this KFCD or the FCD restoration factor is providing us is if you have a rate, it tells you if you know the K, you calculate the delta P of FCD if you know the density of the mixture passing through. So the difference between this K and the pressure loss coefficient is the pressure loss coefficient is unitless or dimensionless, but K has a unit of a meter square. And the difference is pressure loss coefficients. You need the area of the nozzle to calculate the delta P. And the problem is most service providers would not provide the user the A. And it's kind of a secret part of their design to give you the area of nozzle. So for this software, you only need the K to calculate. And if service provider is using the CFD module, only provide the user on the operator side or on any side only the restriction factor for him to go and use the Eushaw software to design their wells. To create the unified model in Eushaw software, we come up with this correlation for restriction factor. And you need these 5 kappas from kappa naught to kappa 4. And by having these based on any Reynolds um, number, you can calculate KFCD. So one may ask us, why this equation? Why not just function of Reynolds? Why not just function of log Reynolds? Why we have to be inverse of log of Reynolds? So look at this curve, and in this curve, we see it's very relevant for this aspect to use the log of Reynolds, because you can say between this number and this scale and this orders of in the log scale is very linear, and after this number it's very steady state, and there is a change here. So that's why we use log, and it's very consistent for even pressure loss coefficient to use log. But the inverse is kind of an idea that we brought in. And why we use inverse? Because as you see here, pressure loss coefficient and also restoration factor at the smaller lane nodes is very um, it's changing massively, and as the Reynolds number is increasing, the change is dropping. So really, by having the log of inverse, we want to reduce the change as the Reynolds numbers approaching the high numbers. And this is type of the matching you can see. This is the inverse of a logarithmic Reynolds for one FCD that modeled with a CFD inside the Eushaw package. And you see the changes smaller Reynolds is higher. So this is inverse, so this is a smaller Reynolds. And you see the change in the higher Reynolds is less. And you see once you compare it, convert it to in the format of Reynolds, that's what we see for the pressure loss coefficient or this restriction factor, is really following the trend of the change of the FCD resistance factor. And you can give it a try. If you just want to do log of Reynolds or Reynolds, it's impossible to match this behavior. So by having this, now let's go and see how we can model this by using the Eushaw Dynamics software and import it into the main system, main reservoir model. Now we want to show how to use the CFD to model the geometry of this chamber type FCDs, and then how to calculate the parameters that we can export into the model, which software does really. So to use any options in the flow control devices modeling, we have to come over here, and there is a option here that says flow control devices, and by clicking here you say add new FCD. So I already have two FCD ones that been run for this example, but this FC3 has just been added. So then you have to come FCD model, and then in here you have to say I want to use Computational Fluid Dynamics to model this. So no experiments, nothing, just this, and my chamber type. And chamber is my FCD type, as what we discussed. In here, you put different dimensions, and you need to put the chamber width, the chamber height, and the channel height and the offset. And you also need to put a thickness, which is the dimension normal to the screen, and also you need to put how many of these chambers you require for this example, for this FCD. So for example, for the select FRRF 3.2, there are 7 chambers for each nozzles to get in here. And for example, 0.8, it's 3 number of chambers. But for your case, and you design a new one, you can call it any name. You can call it X1, for example, and you have 20 of these things. Then you come over here and you put number 20. And the nozzle per joint, because these chambers come in the series and there's a nozzle that you get in and you get out. So it means how many of these you got for every joint. So for example, we got 3 of these series of chambers, so you put 3 here. And by just putting these dimensions, you don't need to do anything further. Tolerance, relaxation factors, anything regarding the CFD have been coded in the way that comes for any dimensions calculate the best fit for those factors. So you don't get any convergency normally, like maybe one out of these cases you may have some issues, but the software jump over those. And I have example of that convergency concern, and you're gonna see. So the software comes and take this chamber or this series of chamber and run it for the series of Reynolds or series of the velocity that you get in to this chamber to calculate this pressure loss coefficient or the resistance factor, because that's Reynolds dependent, and for one flow you only have one Reynolds. And you click here start simulation, and then once you do it, after like about 5-10 minutes, you have that for Reynolds. So I have one case I'd already run here. So this is for this case, and the results tell me the pressure drop in the log scale versus Reynolds. That's just for the users to see how that things are changing. But the thing is important is here. This is the pressure loss coefficients, and we see it comes down and go up like as what you show for like the Baker Hughes select one. And so normally all of them have that sort of a behavior. And this is what we need. So this is the resistance factor. And you see the software comes and curve feed this line over these. And you see this up and downs happening because it's a simulation thing. But we need to curve fit it. And you really don't need to know the parameters, because if you export this software, just take those parameters and name it as one FCD with that correlation and use it in the software. But if you want to see what are these factors are, and this is the correlation that we previously talked about, and these are kappa naught to kappa 4, the factors. And if you want to do something else other than using the Eushaw software, you can put in Excel or whatever. You can use those factors. So by doing this, we have the geometry we assign. We just put a few numbers, we run the case, and the software automatically gives us the correlation parameters and required. In some cases, you may have some of the cases that software reach convergency and jump over those Reynolds of velocity. For example, here is exactly the same of this Reynolds. And so the good thing about it is if you even jump over these, you have enough data points. And one or two cases you couldn't run it with this automated convergency optimization technique that we have in this here. And you can have pretty consistent curve fit over here that you can use in the software without any losing any accuracy of this of using this CFD module. So by saying that, I'm done showing you how you can easily model any geometry. So this example was for chamber that we talked. There will be future example that we're going to talk about venturis and effect of erosion as progressive erosion on these and flashing in these cases. But this is the first example that we start talking about, and it's only start with the simplest FCD, and that would be the chamber type.